Okay, well, welcome to this week's Graphics Programming Weekly Meetup. We're covering Chapter 1 of the vkguide.dev. We're doing the second half of it, where we're covering render passes in the main render loop. So let's dive right into it. Last week we covered, commands and commands buffers, but this week we're going to be actually making the things that go in those commands buffers. So render pass in Vulkan is an object which defines the layout of the render targets. When you want to render something on a GPU using the rasterization pipeline, you have to specify the output destination, specifically an image, while the shaders will tell us what gets written into the image. It doesn't tell us anything about the image. So the render pass encapsulates all of that state. It's unique to Vulkan. I don't want to say it's a great concept, but it does formalize a pattern you see in other APIs where you have a bunch of render targets that you bind and unbind, and the render passes make it very explicit, which is what Vulkan is known for. When you create a render pass, you're only defining the layout and type of things that go in it. You're not defining the images that actually get rendered to. To do that, we need a frame buffer. This frame buffer is the bridge between physical hardware memory and the abstract render pass description. When we want to use a render pass, we begin it in a command buffer, and then we end it, and then and any rendering commands we want to go to those images in the frame buffer that correspond to the render pass we created would be inside of this. So while the Vulkan API is not considered stateful, there is a bit of state here in that you set the render pass, you begin it and do your render commands, and then end it, just like pushing and popping on a stack. So when you begin a render pass, you don't just begin it, you have to specify the frame buffers you're going to use, which is when that bridge gets connected to the render pass, and the clear color. So if you want to clear the depth and color to 0 or black. For our first chapter, we're just going to be changing the color dynamically. We're not rendering any triangles. So that's how we can tell there's something happening on the screen. In Vulkan, there's a concept of subpasses, which are very useful for mobile GPUs, but aren't very useful on desktops, so we won't really cover them. We have to have one subpass to use render passes, but it'd be kind of like it's kind of the empty subpass where it doesn't just do anything on its own other than fill in the checkboxes necessary for the API. So the nice thing that render passes do for us is they perform image layout transitions for us. So when you enter and exit a render pass, you can specify the layout an image is in before and after the render pass. Instead of having to do it manually like you would have in without render passes, we can say that, at the end of a render pass, we're going to put it in the layout that's optimal for presenting to the screen. The reason why we want to do that is images on a GPU are not stored like they are on a file. They're often stored in a way that's either optimal for, it's optimal for some kind of access. Maybe it's for a depth stencil access, or maybe it's a color access. So writing colors into it versus writing depth values. The GPU will lay out the memory differently, which means if we want to use an image for a specific use case, we want to make sure it's in the right format. There's compressed textures, and that plays into this whole concept. There's really only 4 layouts that we care about for this first chapter. The undefined layout means there is no layout. It's not a layout, it's a saying that we don't care what the layout is. The color attachment optimal is, like I said earlier, the layout you want if you're drawing to something or writing color pixels into it. The present source KHR, this is the one we want to have our images end up in for presentation to the screen. And we have our shader read only optimal. This is what our textures, like our albedo and diffuse and all the color textures we sample from to draw models would be in. So now let's go set up a render pass. We definitely need to add the necessary structs. We're just going to have a single VK render pass object and a vector of frame buffers. So we'll slap them down after our command buffers. We also want to have our functions that do the setup we want. And then we need to call those functions from the init function here up here. And where is it? Is it? Yeah, it's here. Cool. So now we can go and add those functions. So the render pass needs to be created before the frame buffers, because to create a frame buffer, you need the render pass it is going to be used with. A quick note is there's quite a few objects in Vulkan that aren't a object to object relationship. They are a layout to object relationship. And it's kind of complicated, but it basically says that I have to create a frame buffer with either a specific render pass or one that's compatible with it. We can talk about that later, but for now, we need to make this here before we create the frame buffers. When we want to use the render pass, we're going to have to give it a list of attachments. These are the images we want to render into. So our color attachment will be the primary thing we render our output to. In the future, we will have a depth buffer attachment, and it will have slightly different layout. So it's the format, we want it to be in the format of the swap chain image. We got that earlier and stored it in a variable. We aren't going to be doing MSSA, which is what this variable is for. Here's what the render pass does for us. We have opload and opstore. This is what happens when the attachment is loaded at the start of the render pass and what happens at the end of it. So what do we want to happen to the contents of the attachment when the render pass ends? So when we're starting the render pass, we want to clear it because we don't want any of the previous frame to be visible. And when we're done, we want to store it. There are other things you can do. I believe IntelliSense will help me. OP, no, it won't. Never mind. So other forms are like don't care, which means it doesn't specify what happens. It could clear it, it could write it, it could do nothing. Since we aren't doing a depth or stencil here, we don't need this. But we do need to set it because we are not using it. So here's that image layout, the initial and final. So we're going to start it in the undefined layout and end it in the present source KHR. This would be optimal for presenting to the screen. And in fact, I believe you have to have it in this format. You can't leave it in, layout general, which is a format. So we have our attachment. And because Vulkan is verbose, we have a attachment reference, which is just, there will be an array of attachments, and this is used to refer to the attachment array and is used in the subpass description. So the subpass is described with an index. the color attachments index, or an array of color attachments, and you use the index here to link up what the subpass is using as its color attachments. Yeah, so someone in that chat asked, it almost feels redundant that both frame buffers and render passes exist. Yeah, sometimes these things feel verbose for the sake of being verbose. And I cannot say that I enjoy this part of the API, render passes and frame buffers and subpasses, especially subpasses, because I don't do mobile. This is the one subpass we're creating. I thought there'd be more to it. I guess not. Yeah, we want to use the layout as color attachment optimal, because that's the thing we want to write into, and we want to make sure it's optimal for writing. So when we're using this subpass, or when this subpass is running, there is a using this color attachment, and this is saying what the layout that color attachment. Man, this is very hard to explain with words only. So moving on, we can actually make the render pass here, and we create our normal create info struct, fill out the S type and whatnot. Here we specify the attachments we're going to use. So we have this big boy right here is our attachment, and we hook it up here. And we can have an array of them, but here we're just having a single one, so we can just take the address of it there. And we have our subpasses, which we do the same thing, but we have here. So then we create the render pass and store it into the object we created. So now let's go create the frame buffers. Copy and paste. We have to specify the render pass that is to be used with the frame buffer. So whenever we want to draw, we need to make sure that the render pass we bind is compatible with the frame buffers we want to use. Usually that means using the exact same thing, and that's fine. A frame buffer is really like a struct that holds a pointer to a image view. It has some information like the width and height and layers, but on its own, it's just a pointer to more things. So we have to create as many frame buffers as we have swap chain images, because we need a frame buffer per image in the swap chain. We can't just we could create the frame buffers on the fly, but in this case, we know that there's going to be, n swap chain images, so we can just create them ahead of time really easily. The format for it is like you've seen before. Now here we have swap chain image count, this is a vector of VK images, and we create the frame buffers based off that size. And here we're creating a new vector with that size. We could do something like this instead, but I think that's a little clear, but as to what's going on. But regardless. And then when we create the frame buffers, because we're changing which image view we're using, because as it turns out, the frame buffer doesn't refer to the image directly, it refers to a image view. We specify the image view before we're creating it. So we're reusing this struct here 3 times over and just changing the p attachments. When we render this, the swap chain will tell us which image view to use. So we'll use that to figure out which frame buffer to use. We got to clean up after ourselves as per usual. Is it up here? Yeah, it's up here. Oh, okay. That looks correct. Does it compile? That's all I care about. Yep, it compiles. Woo. So now we can move on to the main loop, which is where we can actually start getting a drawing loop going and seeing stuff on the screen. So synchronization. In Vulkan, synchronization is explicit. You have to tell the CPU and GPU what happens when, where, and how. We can control a lot of things, and we have several different mechanisms in which to add that control. Some of them are very fine-grained control over the GPU, and others are very broad strokes. Probably the most broad one is the VK fence. The VK fence is for CPU to GPU synchronization. When we submit a command buffer with VKQ submit, there's an optional fence parameter, and that is how we can tell when that command buffer finishes executing from the CPU. So we have a nice timeline of things going on. Our CPU records a command buffer, submits it, adds a fence there, and that kicks off the GPU to do stuff. And to make sure that the CPU doesn't get ahead of the GPU, we call wait for fences, which blocks the CPU until that fence is signaled. The term signaled means, well, you can think of it like a Boolean being set to true, but in this case, it means the thing has finished executing. Once that wait for fences returns, we can go back to doing stuff on the CPU. And the pseudocode for that here is we have our sum operation, my fence that we create. Then because this kicks off work, this returns immediately after kicking off work. It doesn't wait for anything. In Vulkan, many of the calls to get stuff happening on the GPU are asynchronous, meaning they return immediately and let the CPU continue doing stuff. To make the CPU wait, we call wait for fences. And once that returns, this blocks, FYI, once it returns, reset fences is necessary to be called because we have a signaled fence and we need to return it back to an unsignaled state, and that's an explicit operation. So the second type of synchronization that's more fine-grained and necessary for our purposes with the swap chain, that is a semaphore. It is for GPU to GPU synchronization. Specifically, a command buffer gets submitted and we want it to wait for another command buffer to finish executing, but we don't want to use a fence that requires CPU intervention. We can use a semaphore to hook up the start and end of two, well, what they're called is queue operations, but I'm going to call them command buffers because that's easier to rationalize what that means. So there is you create a single semaphore, but to use it, you have to specify both the signal and wait parts of it. You have to use it in one queue submit as a signal and another queue submit as a wait. It's a bit like describing the flow graph ahead of time. So you can kind of imagine it like a tree where you have, we have these two semaphores here, and we have some alpha operation, which doesn't depend on anything. When the alpha operation ends, we want the beta operation to start. And so we signal this semaphore here, which the beta operation will take as a wait semaphore. But when the beta operation finishes, we want to start the gamma operation. And so here, when gamma operation finishes, we're done with whatever we're doing, so we don't have to signal anything. We have to make sure it waits on task 2, the semaphore. So here we're specifying this graph of execution. What's tricky is you're not specifying it and then at the very last call submitting it all at once. You're actually specifying it and then setting up the submitting it, then specifying it, then submitting it, so it's happening real time. The other tricky thing is that this semaphores are useful for managing work across queues, i.e. the graphics or the computer transfer. So you'll oftentimes see them used to say, oh, well, my transfer operation has finished. Now let me go and render with it. So that's semaphores in a nutshell. Now we have our render loop. Our render loop waits on a single fence for the previous frame to finish rendering. We are going to make it the render loop itself more sophisticated later on. For now, we're just going to keep, we're going to follow this pattern where the CPU does work, it submits a queue, then waits for fences, and then the GPU does work. So it's rather inefficient, but it's much simpler to use and explain. So at the start, we have to request an image from the swap chain. Once we get the image index, we can then but we can record command buffer containing the rendering commands we want. And then we specify the render pass and, well, the frame buffer, and then by extension render pass. Actually, no, we do specify both the frame buffer and render pass in this command buffer recording. Then, oh, okay. Yeah, once we finish recording, we submit it, we present it, and we go back to the top of the loop. So now let's actually go implement this. We'll need some more objects, the semaphores and the fence. Go back here and get our functions going. So we want in the init function, we definitely need to create our synchronization structures. The synchronization structure, the fences and semaphores are probably the easiest things to create in the entire API. Semaphores literally have no flags. I don't think they have any flags. Actually, no, they do. But Vulkan 1.0 semaphores just have this. There's no like customization going on. Fences have a little bit more, and their flags have this signal bit. I find this comment woefully inadequate because it doesn't explain why we need this. It is saying that we want to create the fence signaled, meaning the fence starts its life as a true statement or a true value rather than a false one or a 0. And this very specific reason we do that is that the very start of the frame, wait, is there a draw loop that we just, yeah, here. At the very start of our frame, we wait on the fence to signal. The problem is, if the first thing we do is wait for a fence to signal, then the CPU blocks here and sits there waiting for the fence to be signaled, yet we have done nothing to make the fence be signaled. We haven't submitted any command buffers and put the fence in on with it with the queue submit. So this would just block here, and even though it has a timeout of a second, waiting a second for your game to start kind of sucks on every startup. So instead, we create it as signaled, so it starts as a true state, meaning that our draw function immediately, when it gets to the wait for fences, goes, okay, well, it's signaled now. That means I can go on and actually do stuff. Then we reset the fence back to 0. We have timeout. I mentioned that. This is in nanoseconds. So if we put the commas in, you'll see that it is 1 billion seconds, or one second. If we set this to, I don't know, max uint 64, then we'll be waiting for a very long time. But when we set it to 0, it actually returns immediately. And that might be useful to check if a fence is signaled without waiting on it. But, well, the API designers realize that too. And so there's another thing, a function called getFenceStatus, which does exactly that, where it just checks the value and returns it. It doesn't wait for anything. But so now that we've successfully waited for the previous frame to finish using our fence waiting, we will want to acquire an image from the swap chain. There's a lot of parameters here in this function. We have to specify the device and the swap chain and a timeout parameter. Again, we're using 1 second. Here, we give it the present semaphore. So this function here is a function that will signal this semaphore when the condition is met. And what that condition is that the swap chain image is available to be rendered to. So in a more basic API, this function would wait until the image is ready to be used right now. But in Vulkan, we actually, like, if we have some function right here, the function right here doesn't actually know if the image is ready to be done. We have to use the present semaphore to wait first, because it's actually telling us when this function returns that this image will be ready next. It may not be ready yet, and we need to make sure to wait on this present semaphore. This is a fence parameter, and it has its uses, but for what we're doing, we're not going to use it. So we're just using a null pointer here. When this function returns, we'll have the index of the image. We won't know when that image is ready to be used until, well, we won't know when it's ready to be used. We have to wait until on the present semaphore. The image index is just a uint32, and it's referring to the one of the indices in, like this vector here, which is the size of the swap chain images. So, or both of these actually. So if I had image index 2, then it'd be the second image or image view in either of these variables. And that's what this variable represents. It tells us which image is going to be used next. So then we can index into our own copy of the VK image and VK image view buffers or vectors. So now that we've gotten the image we want to render to, we can start recording our commands. We're just going to add it into our draw function. In the future, we may pull it out into its own function. Before we can start rendering, we need to reset the command buffer. This says, hey, okay, put the buffer back into the 0 state, so there's nothing in it. Don't free any memory, though. We're going to use that very shortly. Now we're going to do the command buffer begin, and there's some fun things here that we got to explain. Beginning the command buffer, tell the driver we're going to use this and start recording commands into it. P inheritance info is useful for secondary command buffers. Since we're not going to use it, we're not really going to explain it. There is a useful flag for our situation. Because every frame we record a new command buffer, we submit it once and then throw it away. We're not going to reuse it. So if we can tell the driver, hey, we're only going to submit this once. So the driver can do extra work on it if they want to, because they don't have to preserve anything when it's consuming the command buffer. They can muck it up however, the driver can muck it up however they want, because we're going to reset the whole command buffer and rewrite it afresh. So call the begin command buffer. That means we can start drawing commands. So I'm going to copy this line last because this is the thing we're wanting to do, which is beginning the render pass. We first has to set it up. this is where the actual fun drawing we're going to be doing this chapter is. We have a clear color. A clear color is a union, and it's kind of wacky to initialize. That's why there's these double braces here. But what we're going to initialize it with is 0, 0, flash 1. And this is going to be a color value of, well, the red channel's 0, the green channel 0, and the blue channel is going to be the sign of our frame number divided by a constant. So flash is going to be a sine curve with that's been absolute valued, so it's always positive. So it's always going to be between 0 and 1, and it's strobing, and our frame number increases 1 every frame. So this should, at 60 frames a second, that'd be, okay, well, you can just see and time it. I'm just thinking that should be about 2 strobes a second. Maybe I'm thinking weird. Anyways, now that we have our clear color set, and if we have a depth buffer, we want to set the depth clear value to here. We're going to do our render pass begin info, and this is the structure containing the render pass we want to begin, the area of the render pass, so where in the frame buffer we want this to be. Our window extent is the size, the width height, and our offset is the at what, the top left corner? I think it's top left corner. Might be bottom left. No, coordinate systems are always so hard to remember because every API does it differently. I think this is top left corner. So this is saying how many pixels from the top left corner should it be on the X and Y axis. Maybe it's bottom left, who knows. Then the window extent says, hey, we're going to render this size, and it's going to be it's the same as the window size. The frame buffer we're going to use depends on the swap chain image index we got above here. So this is the first time we're actually pulling in the exact frame buffer we want to write into. Okay. Someone linked the, yeah, okay. Sasha Willems has a coordinate diagram, and Vulkan is top left, whereas OpenGL is bottom left. So that answers that. Thank you. Now, back to the render pass stuff. We've specified the swap chain, the frame buffer we want to use, which indirectly references the swap chain image, but we need to tell it what the clear values are, so we hook it up. It can be an array of clear values. So if we have 5 attachments, then we need 5 clear color values, or clear values, I should say. The inline here is one of those things that we're not going to be really using much because it has to do with subpasses. Actually, no, don't do that. I want to look at subpass. Yeah, subpass contents. Yeah, so if we were using secondary command buffers, this would not be that, but we aren't, so we'll skip it. Okay, so we've begun our render pass, and well, we're not actually issuing drawing commands. We're just changing the clear color value. So we don't actually have to do anything inside the render pass. In a more regular application, we might have something like this, which, we have command 0, blah, blah, blah. There's parameters here. And this would be our drawing command, or draw call. But we're just changing the clear color value, so that's fine. Now, we have recorded our command buffer. We ended it specifying that, okay, we're going to submit this now. We have to prepare our submit info. So when we want to submit a command buffer, we specify the command buffer, and here we have an array of them. We also specify the wait and signal semaphores. So because we're going to be drawing to the swap chain image, we need to make sure that it's available to be drawn on. So we're going to wait on the present semaphore. And once we're done rendering to it, we want to signal the render semaphore. And this will be used in just a bit when we present the image to the swap chain, because presentation is its own dedicated function. Now, there is the pipeline stage here, and this is the It's a bit underexplained, but that's because it has to do with complex types of synchronization. As far as I'm concerned, fences and semaphores are actually relatively simple. It's the pipeline stages that are where Vulkan synchronization becomes hard. So we're just going to use this magic value of color attachment output, give it as our destination stage mask, and then submit our command buffer. Now we're also going to pass in the render fence we want to signal. And this means when this finishes executing, this fence gets signaled and the fence gets waited on at the very top here. So when the draw function gets called the second time, it will make sure that this submit has finished. And well, we're almost done. And the last thing we have to do is present the image we've rendered to. So we create a present info KHR because it's swap chain. Swap chain is an extension. It ends with KHR. We specify which swap chain we're presenting. So we have our swap chain parameter. You can present multiple swap chains. This could be a function you call once every 60 millisecond, 60 times a second or 16 milliseconds. And if you had like multiple windows, that would be a use case for having multiple swap chains, and you could present them all at the same time. Here we have our wait semaphores, and this is what we want to wait on. Here in our queue submit, we're signaling it, and here in our present, we're waiting on it. So this makes sure that the queue present KHR waits on the queue submit, as in the command buffer execution, to finish. So we're not going to present until after we've finished rendering the image. We're also going to have to say which image we're rendering. So which of these swap chain images, and we're doing that by index here. We call the function on the graphics queue, same as with the queue submit. I didn't mention that before, but we're submitting work onto the graphics queue. And then we're presenting that image that we just did on the graphics queue too. And then at the very end of the frame, we increase our frame number so we can exit. We can do our draw function, go back to the top of the while loop, pull our events, and then repeat. So if I hit F5, it should compile magically and run and start flashing. So we got our blue flashing, which is slowly fading in and out. It's not very stroby. To make it more stroby, I'm going to do this. I'll do that. Okay. I want to see it flash faster. Yeah, there we go. So does anyone have any questions about what we just did? There's a whole lot to digest there. Oh, I have. Feel free to turn off your mic. Not. Oh, I didn't destroy the. Okay, so someone asks, do the fence and semaphore signal at the same time? I want to say yes, but what that means is different. For a fence to signal, or a fence signaling is something that the CPU can detect and act upon. We could have the VK, wait for fences right here, and the CPU could act on it. The semaphore signaling is only visible on the GPU. The only way we can act upon it signaling is with this queue present. That does actually mean there is a bit of a race condition here, I think. When we submit the queue, we use this wait semaphore here, and that gets, actually, no, I don't think there's a race condition. No, maybe there is. because I'm getting into the weeds. Q present KHR is waiting on this wait semaphore to signal. And I need to double check this, but if the Q submit finishes running, and then up here we have our wait for fences. And so the queue is finished, the wait for fences, the reset fences, we do all the work, we get the next swap chain image. We know that the present semaphore is ready to be used because when we waited for the fence, that made sure that the queue submit has finished, which means that the signal semaphore here, the present semaphore, has been waited upon and successfully done that. But when we do the queue submit to the queue present, there isn't any guarantee that this render semaphore is actually done yet. So we might be trying to double use it. I think it might actually be protected by the fence again. Frankly, with a VSync and the fact that we're rendering only a clear color, it's not going to be an actual race condition. The GPU is going to finish it way before then. Well, in practice. Yes, the question clarified to mean, do both fence and semaphore get signaled at end of queue execution? Yes. So both the semaphore and fence get signaled at the same time, which is the end of execution. The fence gets signaled not when this function returns, but when the command buffers in this present submit info have finished their work. All the drawing commands in them have been executed and finished executing. That's when the fence and semaphore get signaled. So apologies for that confusion.